Okay, so today we talk about the Bluetooth Lab. We talked earlier about Bluetooth itself as a part of, one of the wireless communication protocols. And so it will be a relative short lecture here, but we talk about Bluetooth, and we want to implement it by in our final project, right? So we want to use Bluetooth to communicate from the remote control to the robot and back. So let's just first talk about the setup. Well, now you really need to work with your Arduino board, right? So you want to program that through the Atmel Studio, and here is some indication of what you would need to do. And there's a video link. So at the time I checked it, we made a video. So you really have to follow that particular guidance, and that is how you set the Bluetooth modules up. So this time you actually have to communicate with those Bluetooth modules directly to program them from your laptop to set them up. So that is, that's just what it is. So in the video both the boards are set up simultaneously, but since you just have one Arduino board, you would then first set up the slave and then the master module. So you have two of those. You have that with you, so here they are. And and there's some tips, so look at that video. It's just a manual procedure that you need to go through to get it to work. And so during the setup you keep this pin pressed down using a clipper in order to get it to program. Yeah, that's what it is. So the video will tell you how to pair those two modules, because that's actually the important thing. So let me go back once, or here we have the copy of those two. So what you have been doing is you have been pairing, after you have gone through the video's suggestions, right, and how to do this, you've paired both. So they agree now also on so they both have an address now, and they can recognize one another. And don't forget that there's many more Bluetooth communications going on around us, especially in the lab when the other students are doing the same stuff. So so you want to make sure that those are paired properly. So once that's done, you need to connect those in the proper way. So the Arduino is on your robot, so you make that happen. And so this is a very manual procedure up to that point. So no programming has happened up to that point, nothing. So you really connect through the Arduino board with the Bluetooth modules, and you set them up, and that's it. So that's what task 1 is about. So you want to test the Bluetooth functionality in the loop-back mode. So for example, send a character from the remote side with the OLED, receive the character at the Arduino side, transmit from the Arduino side back to the OLED side. So if you do this, you obviously need to program, right? You need to program some code and receive it back at the OLED side and display on the OLED. Now, task 2 would be to to create a real communication protocol between the two Bluetooth modules. So once you have tested just the way to send over a character and get it back, well, now you need to think about how you want to use this communication link in your final project effectively. So for example, the protocol must be such that the data is sent out as packets containing a header and then data. That's how you should do it. So the header can now tell the receiving end what kind of information is contained in the data. So for example, here we have a couple of examples, and it will also explain the data length, so you know how many bytes to expect at the other end. So that's very straightforward. So the header will be formed by, say, a 1 byte data type and a 1 byte data length, just to make things simple. And for example, the data types can be joysticks X and Y axis, or the sensor distance values, because what we will be doing is at the robot side you have sensors, and so the sensors scan effectively by going around over an angle back and forth. They scan the direct environment. So you will have code written at some point that then is able to detect obstacles because you want to do collision avoidance. So that type of distance values can be sent back to the remote control, for example. At the same time, if the user wants to use a joystick to go in a certain direction, then you may want to transmit, once you have translated the joystick analog values into direction information, which is all up to you how you do that, then because you want to make smooth turns, for example, and so forth, right? So then that information is interpreted, well, it needs to be transmitted, is then interpreted at the robot to instruct the robot how to go. Now, once you have experimented with this, and this is just, and this is only about communication. You don't have to implement yet, the robots to drive and so on. But you would like to make sure that you can communicate, and you need to set up that communication protocol. Now later, if you want to make it more efficient, right, you can compress the header to 1 byte, where, for example, the first 4 bits of the byte represent the type and the last 4 bits represent the length. You could do that. That's a bit more efficient. You do whatever you do. So depending on the data length, then a corresponding number of data bytes is going to be sent in a packet. And so the whole idea is that you set up a general type of protocol, communication protocol, which that you are designing. Like the CAN protocol was sort of set a priori, right? But you are creating your own application communication protocol, but you would also like to have this kind of general with this header, the data length, but that you recognize from the CAN protocol as well, and then the data that you transmit. So that's the type of stuff that you would like to create, and you again are going to create a library for that. So that's what we would do. And then so we set up in task 3 the joystick, because that's not too hard. And then you would like to experiment already, maybe to display, set up the joystick to display. Anyway, you can send the X and the Y axis value on the OLED. You can display it over there, for example, so you can get the joystick to work for you with the analog to directional information translation that you decide to use for now. And then use the Bluetooth to transmit the joystick values from the remote side to the Arduino side. And for example, set up a LED at Arduino side and change the brightness of the LED according to the joystick Y-axis values. Something very simple, just to test it out. And then transmit back the joystick X and Y-axis values from the Arduino side to the remote side and display it on the OLED so that you are verifying that the communication works fine. That's really what this is about. So this actually should not be too hard of an assignment. Because maybe the hardest part is really setting up and and pairing those two Bluetooth modules. And once that is done, things will start. You will notice that with the experience that you have right now, you ought to be able to really get this going forward. But let's have a look at the task 1 guide. So we will be using a simple non-blocking UART, and we're using an ISR. We explained it in the previous MCU course, so we want to use this, but now we want to use a simplified UART library. And that's because the fscanf and the fprintf are blocking, and we do not want to do, we really don't want to have that. So even in the previous MCU course, even though we make parts of it non-blocking, there's still some things that may not be optimal in that regard. So We have a simplified UART library that the next slides show. And so we use the interrupt-based UART to make sure the program doesn't need to wait, right? So we definitely want to make sure. So this is the UART.h file that we use. So initialization, transmit, receive. And initialization is just straightforward, the usual stuff that you need to do, the baud rate, etc., the right kind of settings that you should have added some comments here to explain what this all means, but that is what we do. For transmit, it's very straightforward, very simple, nothing difficult. We just have a while loop here to wait, so that we can, because you want the transmit buffer to be empty, of course, and once that is done, you can put the data into the buffer. For the receive, again, a super simple thing. You will call this receive when the ISR tells you, right? Then you will call this receive, and again you always put these types of things in there, right? So while the data still is coming in, even though the UART should not have. If you use an ISR, then you of course know that the data has received. But anyway, so for good programming, you definitely put this in, and then you return the data. So that's it. Very simple UART. And then when we look at the car side, then inside the ISR, you can, for example, receive the character and send it back using the USART receive and transmit that we just saw. Now, yeah, so that's what you could do. Yep. Oh yeah, the remark that I would like to make here is that obviously, as I've talked about before, it's much better to have an ISR that has just a very few instruction cycles. But in our application setting, we probably do not need to worry too much about it. So we were lazy and we just did this in the ISR. But with good programming, you would just send out a ready flag, and the ready flag will be catched in another loop in the main program that then will do the receiving and sending of characters. Just to let you know about this. So just to make sure that there's always levels of refinement and optimization that you would like to think about, especially if you're going forward and make this robot even more cleaner and beautiful, if you would like to make it happen. At the remote side, so transmit character, so inside the ISR you can again receive the character and send it back, the same kind of stuff. And in the ISR, you can, for example, display the character received or toggle a LED or something like that if a character is received, so that you have some understanding, or you have a visual for yourself that things are working, because you do need to do debugging, and you better, hopefully you program it right away in a good way, but this is a mechanism to at least see that something is going on. So now what you want to do is you want to create two files, like a Bluetooth library that you're going to create, right? So, for example, you can start with sending 1 byte for data type and 1 byte for length. And once this works, try to compress both to 1 byte. Following, so here you have different data types. For example, you call this, you can define this as being this particular hexadecimal number. And this would mean that the date would represent the joystick axis values. So you can just do defines for these specific hexadecimal combinations, and then you use these to actually, so you transmit this or this depending on what the data will represent. And then you have, of course, the length. So let's have a quick look. So for example, we have been looking at the CAN protocol, and again, it would be good to create like a structure if you want to do that. So here we have these defines again. Then we have a new type that we create, which is a BT packet type. Okay, so the type. So wait a minute. So there's a BT packet type, and there's another type definition, which is a BT packet. It's a structure that contains a packet type of this particular type. So it's a double sort of an indirect definition. We could also have just simply put uint8_t right here, but I guess we didn't. We just liked to indicate that this represents indeed a packet type, which is just the hexadecimal number that we talked about here. So that's it, right? You have a length, and you also have a packet value. The packet value is simply, an array of bytes, and so this will tell you where to find that array of bytes. So now we have defined this type, and at the same time we create a variable of that type, right? We declare that. So, okay, so you would like to have some receive buffer. So here we have a receive buffer, for example, of size 50 or something like that. Oh, here it is, define our buffer size to be 50, so that's it. So we have like an array, and we have also a BT packet _t. Wait a minute, what's that? That's this guy, right? That we just defined. Oh, wait a minute, I'm doing something wrong here. So this is the type, sorry, the type definition of the structure, and now we are defining an actual variable according to that type. Yeah, so is that clear? Yeah, but yeah, I remember that. But yeah, okay. So this is like a variable of this type, and this type is declared as this particular structure as a type. And in this structure, you have several entries, and b_packet. So if you have a type of this, so for example, this variable, I can look at the value of pkt_type, for example, which happens to be a value of this subtype, which we defined up here, which is simply just a uint8_t. And then you can also, so what you will be doing is you will take this variable, and it is just, you can use a dot, for example, or an arrow to indicate which of those fields you were interested in. Well, what other kinds of stuff do we need? Well, we are setting up a buffer. So if you have a receive buffer, you would like to have an index, for example. You would like to know where you are with filling up the buffer, and it's a circular buffer, you probably go around, or however you want to do it. It's just up to you. Once you are reading the buffer, you may want to keep track of course, because you're essentially reading a packet, right? You put it into your own buffer, and the packet starts with a type byte, a length byte, and then it starts with all the data. And but you may want to have some variables. That's what we did apparently. We have some variables that remember what type and length we are talking about. And once you are done, once the buffer has filled up, or you probably only transmit like a few bytes, to be honest. But once it's done, you can set a ready flag. So that means that your loop in the main program can catch that ready flag and say, okay, the buffer is filled up. Let me interpret what this buffer tells me, and I act accordingly. I will then clean up the buffer, and reset the R-ready flag, and also allow, say, the ISR to be engaged again. So you would like to turn, so once this buffer is filled up, you would like to turn off the ISR. So, because you first want to interpret what you read, or what you received, I should say, and then once that is done, you can, reset the buffer completely back to its original state, and you will again make sure that the ISR is again working. All right, so so you have an initialization, the usual stuff, maybe a ready procedure that talks about what you are going to do when the ready flag is indeed set. So what are you doing then? You have a send packet, so you have a packet of this particular type over here. This is the type with that stuff. So you want to send a packet over. So you want to create that type of those instructions. So in task 2, effectively, sorry, we continue here, right? So the initialization, you want to set up the UART and initialize the packet buffer. So you want to do that. You want to here reset the packet receiver for the new packet and re-enable the interrupt, which is what I just talked about with the ready procedure that catches that ready flag that is, well, the main loop catches that the ready flag is set and calls BT ready, and then you execute this stuff. So here we have a send, so transmit each packet bytes one at a time, each packet byte one at a time. And inside the ISR, you receive the character, better would be to do this outside the ISR, as I explained earlier, but you can do it inside as well. In our application, it's not a big deal. And you just store it in the corresponding packet fields so that you can interpret it later on. Alright, so that is effectively about the Bluetooth communication. So let's have a quick talk about the joystick. So first, this is the joystick that you have, and of course joysticks have many applications, and in this particular setting we have a 2-axis joystick, so 2 independent potentiometers that effectively measure how far you have pushed the joystick in the X and the Y direction. Alright, so that means that here's a okay. So what we are going to do is you're going to connect the information that corresponds to the up and down movement and the left-right movement according to over 2 ADC channels, ADC 6 and ADC 7, and you will make sure to initialize the ADC conversion in 2-channel mode, because you have 2 channels to work with. So anyway, it takes an analog voltage ranging from 0 to 5 volts, and this is effectively what happens in the joystick over here. And so in any case, what you need to play with this a little bit, but then you can interpret it as how much you would like to move, which you can do later on, of course. We did this. So what you want to do is you want to set up the joystick as a 2-channel ADC, and those 2 channels are used for the 2 axes. So ensure that the working of the joystick by displaying the 2 axis values, then integrate it with the Bluetooth to transmit the joystick values and display it either at the remote side in loopback, OLED or car side. So you want to figure out how to work with it. And then for the proper functioning of ADC, then connect the AREF pin to the 5 volt. So don't forget that. And this is just some copy of code from the other course, which talks about what you usually do when you do an ADC conversion. So you start one by setting this, then you wait until the conversion is completed by having a while loop, and for example, here's an example of that main program in which you do some kind of conversion. I hope you recognize this. So you set up a bunch of setup settings. Now you need to change this because you want to have a 2-channel ADC connection. So this is just selecting ADC channel 6, but just as an example. But you want to work with 2 channels. You have a prescaler again. You enable the ADC circuit, right? So that's always important. And then you start and wait. You convert analog to digital. So you need to read out the higher bytes. You remember you have an ADC H and the ADC L, and it depends a little bit on how you set this up. But 8 bits precision is more than enough. You don't need to go beyond that. So that's why you can just work with this. So typecast a volatile integer into a floating type data. So that's what we do here. We typecast it with float. And in this particular case, we do divide by 1024. That's 2 to the power 10. Divide by maximum 10-bit value.
Right, you're still using the AC, just forgetting about the other
Okay, that's what it is. Well, thanks. And so that's what it is. Yeah, absolutely. Great. So you're just forgetting about the lower 2 bits, and this is still a 2 to the power 10 value, effectively. So that's what you do. All right, any questions? So there's a whole bunch of stuff going on here, but I feel that this particular Bluetooth lab will start to combine also a bunch of these modules that you have. Like things will slowly start to get together, I hope. Any questions so far? Now, after this lab, we're really in final project mode, right? So there is quite a bit of time. There is this week. We have next week a spring break. You may do other things, and then the week after, I have to decide what I do on the Wednesday. But I may teach on the Wednesday or not. It depends, but not on the Monday. And the lab is open, of course, on Monday, but so you can go there. But the point is, though, that you want to make use of these nice 3 weeks. And hopefully I can answer some questions on that Wednesday or through email. But the point is that that you start to pull things together now. So you can go far beyond this lab, and you can already engage yourself in the final project.